All right, we're starting chapter, well, this is going to be the second part of chapter 12. We're going to get into inference for slope. So today we're going to do a little review from chapter 3, which was on least square regression lines, and get a little bit into what we're going to be doing the next 2 days with this. So, do customers who stay longer at buffets give larger tips? I mean, do people tip at buffets that often anyway? We'll see. Charlotte, an AP Stats student who worked at an Asian-style buffet restaurant, decided to investigate this question for her final project. During her job as a hostess, she obtained a random sample of receipts, which included the length of time in minutes that a party stayed at the restaurant and the tip amount. Here's the data. I'd like you to create a scatter plot and then describe that distribution. See what you remember. Ready, set, go. All right, if you have that, hopefully it looks something like this. Where I've got tip amount, that's going to be my y, my x was time. I think that's a good decision for x versus y because I'm going to make this a little bit smaller so it actually fits here. Your time, we're trying to see if the time kind of determines the tip amount. Now, describing it. If you recall, our acronym DUFS. Review. D stands for direction. And this is like positive or negative. U stands for unusual features. Usually some sort of outliers or clusters that are obvious. F, the form. Is it linear or nonlinear is pretty much all we're looking for. And then S, the strength. You can learn more about the strength once we figure out your correlation value, the R value. But we can look at it and make our own estimate based off of the line. So our options really are strong, moderate, and weak, or somewhere in between those. So if you looked at this and you thought that it looks generally linear, I can kind of make this linear shape to it. Looks like it to me. Maybe you said something like what I said. There is a fairly weak, I'm going to say fairly weak. I look at that, I don't think it's strong. It's linear, but I would say it's fairly weak, positive linear relationship between time spent at a restaurant and the amount of time left, or amount of a tip left for customers. So I don't have any specific unusual features, so I don't even have to list that. But I have the strength right here. This is my S. The direction is right there, and the form is right there. And I have context. So that's a review from chapter 3. Now, we're going to be utilizing that today. We want to make some inferences about slope. So just like we're able to estimate or test things about like the true mean, the true proportion, we can do that with the true slope. What is the actual slope of the population? We're going to use sample data to help us estimate that. In order to do that, when we're going to do inference with this stuff, there's some preliminary pieces we have to do, including making a scatter plot, like we just did, finding the R in least square regression line. We can use a calculator, use tech, or if we're given the computer printout already, analyze the residual plot and the residuals themselves. So those are all things that we're going to kind of review today and get going here. Now, if all preliminary pieces are good, we can move into inference, either a hypothesis test or a confidence interval for slope, and that is going to be beta. So slope is normally b, little b, but it's the Greek letter beta. Now, this is a new parameter. It is B is our normal slope from least square regression line sample data. So B, capital B, beta, is the true slope of the line relating x and y, blank and blank. All right? So we're going to be utilizing that. Now, quick recap of a least square regression line. Now, if you took that data that we just dealt with and put it into your calculator, I'm going to show you that here real quick. So if you go to your list, and I put in, you can see here all the x's and the y's. Time is on the list 1. Tip amount is on list 2. I can then go to stat, calc. Remember, this is number 8. It's linear regression, but we're doing the a plus the bx form. Okay, list 1, list 2, nothing else. Calculate, boom. Now, that is what I had on this other slide. Oops, sorry about that. And if you look at everything to the right, it gives us our A, it gives us our B, and it gives us R squared and R. Now, we can write the equation of this linear regression LSRL, the least square regression line, which would be y hat, remember this is a predicted amount, equals 4.535 plus 0.0301 x. That's our least square regression line. Now, anytime we write a least square regression line, typically need to identify what each of those parts are. So y hat is the predicted tip amount. That's our goal, is to predict that. X is the time spent at a restaurant. That's not predicted. That's just what we know. The 4.535 is the predicted amount of a tip for a group that stays 0 minutes at a restaurant. So just by showing up, on average, they're going to give around a $4.50 tip. And then that 0.03 is the predicted increase for every additional minute the group stays. Now that's, again, a review from Chapter 3, but we need to know how to do that. We need to find those things to help us estimate things. Now let's review residuals, another review. Residuals are how far off from that least square regression line is like each point on average. So we have an acronym. Maybe you recall it, maybe you don't. It is RAMP, which means residual is actual minus predicted. So you can find an individual residual for each point. So let's just take, for instance, 23 minutes. The person who stayed at 23 minutes. The actual was $5. So if you go back and look at our data, the actual for that 23-minute person, first one is $5. So we can find the residual for that. So this is actual. Now to find the residual, we'd have to take our y, we'd have to find our predicted. So I'm going to plug in, it was 4.535 plus 0.0301, and we want to plug in 23 minutes, and that'll give us the predicted amount, which is $5.23, I believe. Now, if you actually put in more decimal places to make it a little more accurate, it's like 2273. Our actual was over there. This is our predicted amount. You actually have to plug into your predictor formula, your least square regression line formula, to find a predicted value. So we have the actual, we have the predicted. So to find the residual, a residual is, what was it, 5 minus 5.2273, which is negative 0.2273. Okay, so the way we'd explain that is the least square regression line over predicted the amount of the tip left by 22 cents, 23 cents for a group that stayed 23 minutes at the restaurant. Or some version of that. We want to state what that residual is, and whether it's over or under predicted, if the least square regression line over or under predicted, and for what that actual value was. So that's, a residual. Now, you can use your lists to find those residuals. So I'm going to take you back to our lists here. So if I go and have my x and y, I can find, now that I have my equation, I can find all the predicted amounts. So this 3, I'm going to put in as my predicted amounts. So that's going to be equal to, what did I say my equation was? 4.535 plus, it was 0.0301 times whatever our actual x value is. And that's coming from list 1. So I'm going to put in list 1 right here. And if I hit enter, it'll give me all of the predicted amounts. And there's that 5.2273 that we just talked about. Now, to get the residuals, I'm going to go to list 4, and I'm going to find every residual is the actual minus the predicted. So that's list 2, which is our actual, minus list 3, and that'll give me all the residuals. So if you want to find all the residuals easily, that's how you can use technology to do it. Now, we've talked about residual plots, and we're going to have to use those again here today and in this chapter. So we want to make a residual plot. Typically we compare our x to our residuals. Now you could take your list 1 and your list 4, and you can make a plot on your own calculator. But if you're asked to put it out here, typically residuals aren't super like crazy high. So if this is my residuals over here, typically I'm going to go, we want 0 here. I'm going to go 1, 2, 3, -1, -2, -3. Usually they'll all fit in there. And then this is going to be my x-axis. And I guess my numbers went from like 23 minutes all the way to 99 minutes. So if we can somehow get from all the way up to 100 on here, that's how we're going to do it. So I'm just going to go, let's go 10, 20, I think this will work, 30. Oh, gotta go 100 right here. All right, so to not confuse you, this is going to be my x. Okay, and then you can start plotting them. All right, I put those points on there. There's my residual plot. Not perfect, but I have essentially what it looks like. Now, there's something that I want to review here. Residual plots should be truly scattered. Okay, so right now we have about the same on top and bottom. We got 3, 6 on top, 6 on the bottom. That's a good thing. I don't see any clear pattern. So remember, patterns are bad for residual plots. So if you see something like a clear here's a U or upside down U, that's bad. If you see a clear fanning, is it usually what it's called, kind of goes like this, it's very clear, that's usually bad. Okay, residual plots kind of will accentuate any non-linearness to them, and if it's not clear that there's anything else, then it's probably good. Okay, this one's pretty good. Now, the last thing that you might need to go to, and sometimes we actually will with this in this unit, is a residual distribution. Okay, we're taking what we're looking at here and just trying to put them kind of sideways, in, so to speak, where we want to actually make. I'll do it with this. So we can see if there's any normality to it, or if there's any clear skews or outliers. Like if we have a residual that's way like a -10 and the rest of them are all in the -3 to +3, then that's probably like a clear outlier. That's usually not great. We don't want any clear skew or outliers. So I'm going to make my residual distribution here going 0, 1, 2, 3. This is just the value of the residuals. And we want to kind of see where do they all fall. It can help to actually look at your residual plot and just kind of draw your lines across. How many of them are between 0, 1, 1, 2, 2, 3? So I've got 3 in the 0 to 1 category. So in 0, 1, I'm going to go 1, 2, 3. 1 in the 1 to 2, and then 2 in the 2 to 3. 1 here, 2 here. And then the negatives, I didn't add those on here, but we have, ooh, there's one that's real close there. What was that, 99? Go back to our data. Oh, that's not the right one. 99 was 6.5. Wait, the residual for 99 is negative, whoops, well, it's past -1, so it's over -1. So we actually, that one's going to be down here. So we only had a 2 in the 0 to -1 area. I got 2 in the other area, the next area, and 2 in the next area. So these are looking like 2s to me. And that's my residual plot. Okay? Now, I think I maybe drew one wrong. I think this one is supposed to be up here. But either way, if I look at this, it's pretty uniform. It might be a little bit more normal looking if I had that one correctly. I think this one actually, well, that one should have 2. Here and here instead of 1 here. But either way, there's no clear skew or outliers. So it's okay to proceed with this. Okay? We want to kind of divide this up. So I'll make a note of here. You could do it differently. To 4 to 6 sections. Kind of picture turning it on its side is what I was looking at there. And that's the distribution of the residuals. Unfortunately, it is something that we need to check. And it's just an extra step to check. So here's some new stuff. We need to check a whole bunch of conditions for linear regression inference. And I'm going to list them here for you today. And then we're going to just talk a little bit about each one. And then do more with this tomorrow. Now, it does form an acronym, and it's super close to linear. It's actually LINER. It's liner. So I'm going to give a little more detail about each one. So the first one is linear. So for linear, we want to look at the true relationship between x and y to see if it's linear. So examine the scatter plot to see if the overall pattern is roughly linear. Make sure that there are no leftover curve patterns in the residual plot as well. So we check both the scatter plot and the residual plot, which sometimes are given to you. This one, I see some curve in this, the residual plot, so I'm going to say even though it looks linear, it's probably not linear actually. So this isn't even the same data from the two, but the scatter plot looks linear, the residual plot does not. It has to be both. So I would say the true relationship between x and y is linear or not. Second one, I, independent. Still something we're going to be checking. Knowing the value of the response variable for one individual shouldn't help predict the value of the other one. There shouldn't be a connection there. So if you're sampling without replacement, we can check the 10% condition. something similar there. Third one, it's kind of what we just checked with the residual distribution. Make a plot of the residuals and check for strong skewness or outliers. Ideally, we would check normality of the residuals at each possible value of x. Because we rarely have enough observations of the x value, we make one graph of all the residuals to check. So this is where you're going to check the residual distribution. All right, the E is equal standard deviation. Okay, so look at the scatter plot of the residuals above and below. We want about the same. We also want like the largest x value, the largest residual and the smallest residual to have about the same distance. So like, if I'm looking at this residual plot, we go to about negative 7,000. This goes up to about positive 8,000, depending on how you're drawing it. That's close. That's not bad. This one's bad because it's got this fanning to it. So if you go all the way to the farther x's, it's different than the farther y. Same thing over here. We don't want like too much different on the two ends. So we want it to look fairly random, but also spread out similarly. So that's the equal standard deviation. So we want it to be about the same on either side of that residual line. And the last one, random. Nothing new here, but we want to see if the data came from random sample from the population. If not, we can't make actually inferences about the larger population. Okay? So if we go back to our example before, were our conditions met? Well, we can go down the line and we can check each of the things that we did and decide if they're met. Now to help us out, if we define x and y, we can save ourselves some time with each of these conditions. So x was time in minutes of staying at the restaurant, and y was the tip amount in dollars. So by defining those, we can save some time. So first question, we want to state the true relationship between x and y is linear. And we can say yes. The scatter plot is roughly linear. And we got to check that residual plot. The residual plot shows no pattern. Good. Second one, independence. We've done that before. There's 12 receipts. Would we say that 12 is less than 10% of all receipts, even for that day? Probably yes. And I think we're going to assume yes. All right, moving on. N for liner is the approximately normal condition. So we want to say for each x, the y is approximately normal. We did the distribution of residuals, so yes. The residual distribution has no strong skew outliers. We want to state where this is coming from. E, the variability of y's is equal for all. So this is like the standard deviation. Is it equal for all of the x's? If we look at our residual plot, I'm going to show that to you. I would say, yeah, on the right side it kind of goes down to up to a little over 2, down to a little below -2. The left side is not much. It looks pretty random and equal to me. I'd say it's good enough, for sure. So we're going to say yes. Residual plot shows similar scatter for all x's, we'll say. And last one, R. Was this a random sample of receipts? I believe it was stated so. And because of that, we can say all conditions are met. Now, you're going to see why this isn't my most fun thing to do, because we have a lot of conditions and a lot of work to get those conditions met. Okay? But next time we're going to get into talking about some of the parameters that we're going to be utilizing and how we can actually get this data from sampling distributions before we actually get into some inference procedures. All right? That is lesson 12.3a for you, kind of a review for chapter 3 and getting into the conditions for this. We'll see you next time.